All right, so we're going to continue moving closer to where we're going to be doing frequency response plots, which is magnitude and phase for all different frequencies. But this is also known quite well as a Bode plot. All right. And a Bode plot or a frequency response plot is a combination of two plots. It shows the magnitude as a function of frequency and the phase as a function of frequency. And I'll note these are generally done on semi-log paper. All right. So when they're doing this, people generally have the horizontal axis, the horizontal logged axis showing frequency. Okay. And then the vertical axes either show phase in degrees or magnitude in decibels, where we just introduced this. A decibel is 20 log base 10 of what the magnitude is. All right. Now, so what I want to do is to help you to be able to do plots of these things. Of course, these days it's very simple to go to MATLAB, enter in a transfer function and say, okay, compute the magnitude and phase for a whole slew of frequencies and plot it. But it's worthy to understand how to do straight line approximations of these and sketch them, because it shows generally how the structure of these things work. And that's what we want you to understand. So we're going to look at doing a straight line approximation of omega n squared s squared plus 2 zeta omega n s plus omega n squared. So we've been playing with this. We're going to keep playing some more. So from what we've just done, okay, as we were looking at these, the magnitude plot, what's it going to do? So if you look, generally when we do these things, we set them up to be unity static gain. So if you look at let s be 0, that's omega n squared over omega n squared, so that's fine. So let's see what we have. I will note that omega d, omega max, omega n are all in close proximity as long as your damping is reasonably low. And so this is the straight line approximation. You go along, because at low frequency, it's going to be 1 or 0 dB. Okay. And then we go up to omega n, and from there, we drop at a rate of 40 decibels per decade. That's another way of saying a factor of 100. Every time the frequency increases by a factor of 10, we drop by a factor of 100. Every power of s is causing you to drop by, we have two powers of s here. Every power of s is going to cause a 20 decibel shift or a factor of 10 shift in gain at high frequencies. Okay, so it's going along flat. Around the resonance, you're going to get some growth, and depending on the level of the damping, it will determine how high that is. Okay, if you have really high damping, then it's going to, you'll have your growth, you'll have a little blip somewhere up here, say, but then it's going to go, it'll be in relative to this straight line approximation, it'll come down and it'll be a little bit underneath this, and it'll drop. It'll eventually match up with this minus 40 dB per decade. For low damping, you're going to get your resonance somewhere in the neighborhood of omega n, and it goes up, and then it's just, as it comes down, it'll asymptotically approach this minus 40 dB per decade line, or minus a factor of 100 for 10 times increase in frequency. All right. So any underdamped system, here's our straight line approximation, where we're just kind of ignoring the level of damping and stuff. And outside of the resonance, it's a pretty good approximation, actually. Okay, so there's magnitude, and we've seen that. So the work we've just done has shown that. And now let's look at the phase for this same system. Okay, the straight line approximation we use basically says go along at 0 degrees for this system. At omega n, you lose half. So there's two factors of s. For every factor of s, there's a 90-degree shift. So we're going to shift 180. At the natural frequency, you lose half. So we're going to go at 0 up to 1/10 of omega n, and then we'll drop 90 over as we go from 0.1 of omega n to omega n. And then at 10 times that, we'll finish dropping. And this is a little out of scale, I see in my drawing. So let me fix this. It's actually way out of scale, but it doesn't really matter all that much. We'll let this be 100 omega n. These should be evenly spaced, but, oh, they are now. Yeah, 1, 2, 3, 1, 2, 3. That works out. All right. So here we are at 10 times the natural frequency. We will lose, in this decade, we lose the other 90 degrees, and then it levels out. All right. If you have low damping, here's what happens. This flat line kind of continues longer, and then it just dives down through omega n. The lower the damping is, the more it wants to go right up to the edge and then just go straight down. So if you have damping of 0.01, it'll go to really close to omega n, and then it makes sort of a right turn at Albuquerque, drops down, and then it just levels out there at minus 180 roughly. Okay, so here's the straight line approximation. The lower the damping is, the more it will just stay out, and then it comes back into the bottom side. So here it's the phase here is lagging the predictor, and here it's ahead of the predictor. And there we have it. All right. So given that, what's the straight line approximation for a first order system? Okay. And here you notice I put it in a unity static gain form. Let s equal 0, I got a 1. Okay. So the straight line approximation is basically the same thing. We have 1 power of s, meaning we're going to fall by a factor of 10 as we increase the frequency by a factor of 10, or 20 dB. Okay, those are the shifts we get in gain. And so the approximation says go to A. This is right here. So here we did it at omega n. Here we're going to do it at A. And we go straight, and then we fall off at 20 dB per decade. All right, so that's a factor of 10 for every decade of frequency. And this is a very good approximation. This is within about 3 decibels or so here. So in reality, it's going just a little bit below. It's asymptotically coming off the horizontal, and it asymptotically matches up with this minus 20. Okay, pretty good approximation. All right, phase. What's kind of the same thing. Notice before we went to omega n, and we went 1/10 below and 10 times above, right? And we lost, at omega n, we lost half our phase. Well, at A, here, and notice this is where the root is. If you were to solve for this, you'd see s equals minus a. At A, we lose half our phase. So the straight line approximation says go take this a, divide by 10, so it's 0.1a. So you start here, you go from 0, lose 45, and you lose the second half as you go up to 10a. And then it levels off at minus 90. So what do we notice here? For every power of s, there's a 20 dB shift in gain at high frequency. At low, it stays, it's flattened, but at high frequency, you're losing. Okay, and for every power of s, we lose 90 degrees. Or if it's a 0, we add 90 degrees. Okay, now when you look at this, what does this show? Both of these. These would be called low-pass systems. So at low frequency, the strength of the signal goes through. Whatever the amplitude was, the gain in the system is 0 dB or a factor of 1. All right, so it can track a sinusoid. As you start getting at higher frequency, it can't keep up, so the amplitude is going down. And it's losing phase in terms of keeping track with this. If you have a second order system, it's worse. It falls off faster, and it loses more phase. Okay, systems, mechanical systems are naturally low-pass systems. As you get to high frequency, at some point, it just can't keep up. And so as you pass through the natural frequencies of the system, it's saying, I can't keep up anymore. That's what you're seeing. Now, when I say mechanical systems are low-pass systems, I'm talking about you, all right? You are a low-pass system. We're going to prove that right now. Okay, So watch my hand, because that's all you can ever watch. And so I'm going to move my hand back and forth roughly the width of the paper. Okay, so this is a sinusoid as my hand goes from one side to the other. Okay, now I can speed my hand up to a point, and I can still pretty well go the width of the paper back and forth. Okay, now watch what happens as I increase the frequency higher and higher and higher. Okay, so what you hopefully saw is as I went to higher frequency, I couldn't do this whole amplitude. Why? Because there is a terminal velocity that my hand can move at. And that's once you hit as fast as you can move, you can't move any faster. So to keep up with the frequency, since I can't move more quickly from side to side, then your body naturally starts cutting off amplitude. So I'm moving at as fast as I can go back and forth, but I'm cutting the amplitude range. The higher the frequency, the more it cuts off. And that is a natural phenomena of low pass systems. Once you get up to your maximum velocity, the only way you can keep up with the frequency of going back and forth, because you have to run at the same frequency, you have to maintain your frequency, is to cut your amplitude. It's the only way. So when you start seeing this falling off, the machine is telling you, I can't go any faster. And so it starts cutting off amplitude to maintain the frequency, which it has to match. So that's what we're seeing. And so let's see, we're going to take this just a little bit further in this video. So we saw what this one does. By the way, we can put this in classical unity static gain form. If you let s go to 0, you get a 1. But people will often write it in this form. So divide by omega n squared, and we still unity static gain. Now, what would the Bode plot of this look like? So take this and flip it this way. So now I have 2 zeros over a 1. It's really easy. It simply says mirror across the 0 dB line and the 0 degree axes. So going back to here, if this were flipped, it would go to omega n and go up like so. If you look at here for the phase, it would start at 1/10 of the natural frequency, go up for 180 degrees, and level off. So we've plotted it for poles. We can do the plot for zeros. Likewise, if you had a zero, a first order zero, s on a plus 1, no problem. It's just the same idea. For this plot, you get to A, you go up at 20 dB per decade. Here you went up at 40, here you go up at 20. Likewise, for the frequency, you start at 0.1, you go up to 45 degrees at A, at 10A, whatever A is, you hit 90, level off. Same difference. All right. The next piece we got to look at is Bode plot of a gain factor, just some gain K. It's really quite simple. So K in dB is, so whatever your gain is in your system, whether it's 10, 20, 80, a million, doesn't matter, 20 log base 10 of K will give you that K in dB. So suppose you had K in dB was effectively 12 decibels. You want to add that to a Bode plot. All right. Well, you go to 12 decibels and you go boom for all frequencies. Now, a gain is either going to be positive or negative. If it's positive, you're simply at 0 degrees for all frequencies. If it's negative, this would be minus 180 for all frequencies. Okay? And so those are some of the basic parts for making